I think we can start. Okay, hello everyone, and welcome to one of the another webinar in the MIA webinar series that we organize throughout the year. Um, so my name is Salva Daneshkar, and I'm a vice chair of MIA Modeling and Integrated Assessment Specialist Group. And together with Elena Torfs, who is also here, who is the chair of the MIA group, we are organizing together with many other people who helped in the organization this webinar. I'm gonna just briefly give you a very short introduction to MIA and who we are and what we do, let's say, and then hand it to Luis to uh, continue with the webinar. Okay, so we are one of the 50, I think, specialist group as at the IWA, and one of the quite active funds. So we have a large management committee and quite many people who are helping in organizing different activities at our group. In general, MIA is a group that, I mean, the name is also suggests that we are focusing on modeling and integrated assessment of water systems with the idea that the academia, utility, researchers, industry, they all get connected and working in different activities related to the modeling and integrated assessment of the water systems, not related to any specific aspect of water, but the whole water cycle in mostly urban domain. And on the right-hand side of this, you can find some information. I will also give some details maybe at the end. So where you can find more information about us. Of course, if you visit the website, you get more information about all the activities that we do, but some of the highlights of the most probably important ones that we do. So we have quite a number of task groups and working groups at MIA who are active and working on a specific topics. So task groups, a few people who gather to perform a specific task for a few years, and at the end, most of them they will publish a scientific and technical report. You can see on the bottom side of this slide a few. I mean, the most recent, let's say, SDRs published by IWA out of the working groups and task groups of MIA. And most of them, I think at the moment, all of them actually. So the CFD also is available open access, so you can download them freely on the IWA publishing website. Then apart from that, we are also a core supporter behind the organization of the two main modeling conferences in the water domain. So the one being Water Resource Recovery Modeling Seminar, WR Mod Series, and Water Matrix, so Symposium on Modeling and Integrated Assessment. And you see the next ones on the slide. So in June next year, we will go to Barcelona to host the next version of, let's say, WR Mod, and in 2027 in south of France, we will have the next water matrix. And as I said, we are quite active also in the virtual, let's say, platforms. So on social media, on LinkedIn, we have quite an active page where always we share all the details about the activities, events, and webinars, for example, that we organize. But also on the website of the MIA, you can find many details about the management committee, the yearly report that we have about all the activities that we have. So please go and check if you're interested. And if you're also interested in joining one of these activities, for example, these webinars, if you have ideas for organization of some interesting webinars, feel free to contact us and we will make sure that we can find a good collaboration among us. So that was it. So very brief. So back to you, I mean, Luis, for the webinar, and I hope that you enjoy this webinar as we have very nice and good presenters.
Yeah, thank you, Saba. Welcome everyone to this webinar on data-driven modeling in the water sector, a paradigm shift in predictive methods. My name is Luis Corominas. I'm a senior researcher at the Catalan Institute for Water Research, and I'm expert in monitoring and modeling of human wastewater systems. And this webinar will have 3 presentations, and then we'll have a Q&A session. It will last until 4:30. Remember, if you have questions, that you can open the Q&A box and post the questions there, and some questions might be answered on the fly. Otherwise, we'll respond everything when the presentations are finalized. Okay. So to start, let's start with Mostafa Khalil. He's an innovation engineer and data scientist at Stantec Water Office of Innovation and Technology. He works at the intersection of process engineering, mechanistic modeling, and machine learning, developing digital tools and applied research solutions for water and wastewater systems. So, Mustafa, the floor is yours, and you can start with the first presentation.
Yeah, of course. Let me share my screen. Sorry if I got disconnected for a minute. Can you all now see my screen? Yeah, perfect. Uh, so good day, everyone. Thanks for joining the webinar. Today we will be talking about how the shift towards using data-driven modeling in the water sector and being part of your modeling toolbox. So all of us as water wastewater practitioners, we use modeling as a part of our decision making. Either we are operators or designers or researchers. And now today we're gonna view how data-driven modeling shift being part of that modeling toolbox. So over the years and even the past few decades, when we talk about modeling and we talk about, hey, we're doing a model in the water, wastewater, everyone almost means first principles models, where the physical laws like mass balance, chemical interactions, or biological processes are lumped together based on our knowledge, based on the formulas that we know, and they are lumped together into one model. And that model takes the initial state of the system and then also takes some that disturbances that affect the system, like the influent flow, if we're talking about a treatment plant or whatever, and it takes the parameter values too, like the reaction kinetics, and that gives us the predicted system state at another time. So that's how we used to do modeling, and we're still doing it, and likely we will be continue doing it, but that's how it used to be working. And another part of that, maybe a little tweak, is when we just try to simplify these processes. We just literally not throw in everything that we know about the system, but they are kind of lumped or more simplified. So instead of all chemical reaction interaction, they are simplified and the same for biological processes. And now we're talking about semi-empirical models. And as an example of this is a mechanistic model such as the ASM models in the wastewater that almost every wastewater engineer is using it maybe on a daily basis. So these mechanistic models has been the gold standards in our field. They actually try to model a cause and an effect relationship. So that's why we love them. That's why we like working with them because they can understand our mind, our causal mind. Like every one of us has we prefer the causal relationships over than statistical relationships because that allow us to modify or maybe answer some what if questions or hypothetical questions or making an intervention so that we see, okay, now this is the actual case of the plant or that's the actual case of the system. But what if we changed that factor? What's going to happen in the system? So because these models are mainly based on a causal relationships, they allow us to do so with reasonable confidence. And that means they also work outside of the calibration range. Conceptually, you could extrapolate these models. You may have less confidence because the parameters, you didn't calibrate the parameters in another operational range, but you still have the conceptual confidence because you're still modeling the same relationship. So you likely know that the trend might be right, or you have a reasonable confidence that when you extrapolate, things will work out. But this confidence is conditional because it assumes that you understand all the relationships in the system. So, assuming you're modeling a simple wastewater treatment plant like this or a biological treatment part of it, so it assumes you understand all the relationships. There is no process that you're seeing for the first time, or there is no process that you don't understand how it works, or you poorly understand how it works. You also assume that the parameters or the kinetics of that model are constant over time. So for example, when you're modeling that wastewater treatment plant like this, you assume like them, for example, mu max of the AOB or mu max of heterotrophs, they are constant over time. They don't change. Even if you know they may be changes, but you assume there is no drastic changes that may affect how you model your system. And that's a core part of the some hidden assumptions that when you model you start you have it in your mind. And that, of course, the same formulas will hold at all conditions. You don't think that the monod equation, for example, will change, or there is going to be another term that should be added. And the modeling software and the modeling versions are being improved day by day by adding some switch functions, inhibition functions that activate at certain conditions to make sure that the same formula will hold all the time. But actually, when you try to think, why do we build these models? Like, is it like sometimes we may face some challenges? Are the mechanistic models are fit everything that we need to do? So assume look at the things from a bigger system thinking perspective. You're going to see that we have some inputs which are a function of time, system state, which is going to be a result of the input, and also is going to be a function of time, and the same of the output. So if you thought about the inputs themselves, and now we're talking about time t, which is the present, assuming that now if you'd like to model the input and understand more about it, that's kind of an influence generation problem. If you'd like to understand more about the system state, now that's turned into a monitoring and understanding problem. And you would like to model to understand the output or predict the output, so that could help you in planning and decision support. But if you thought about the future, if you want to understand how things go in the future, so that means you will be in, sorry, sorry. So when you think about the future, if you would like to forecast the inputs in the future, that will help you do some resource planning. So, for example, if you can forecast what's going to be the influent generated, what is the influence being generated in the future in the next few days, that will allow you to do some resource planning. For example, shut down some reactors, or maybe you need some extra operators working on site. And same for the system state. If you can forecast what's going to happen to the system state, assuming the changes that you expect in the input, that will allow you to do some asset health and maintenance. And for the outputs, that will allow you to do some process optimization and control. So things they don't fall in the same box with a U model because you would like to do some monitoring and understanding of a system only, and you have only one or a single objective. But no, it works by there are different evolving objectives, and you probably not the same or not the simple type or same type of model will be working for everything. So thinking about these objectives, putting them into boxes, we have process monitoring and understanding, we have asset health and maintenance, we have forecasting, we have process optimization and control, we have planning and decision support. But not every part of this can be done using the same type of models. For example, you can do forecasting using the same mechanistic models. Well, there are some trials to do forecasting using this, but they are require massive amount of data, and they are not giving the results that everyone aims for. But if we think about things the other way, with the huge amount of data that being generated every day and the evolving computational power, and now everyone is talking about probably artificial intelligence, but how do we benefit from that into our field or into our water sector? A little bit introduction about what artificial intelligence is and what is machine learning. So it simply is a part of is artificial intelligence is mimicking how the human do the tasks and how the human do intelligent tasks. So human can, for example, they can talk and understand language. So now we have the natural language processing and some capabilities such as ChatGPT, like everyone is interacting maybe in a daily basis right now. We have some computer vision, and it helps something like the autonomous car, autonomous driving, and we have robotics mimicking how human move. And then we have that no need to talk more about robotics because everyone has seen the or seeing the revolution they are making. And speech recognition, like probably you have it in your pocket and his as a Siri or Bixby or whatever. And all of that are being empowered using machine learning because the human capability to learn new things, to train these models, how it works, how it sees new objects, how it detects it, how it moves, how it recognizes your speech. It's based on machine learning, like, and it's the computer capability to learn from data. And it seems like the idea of the machine learning is what we aim. We have lots of data that is generating on a daily basis. So if we can get the algorithm to learn our water or wastewater data, that will be helpful or that could complement what we do in our modeling. So think of machine learning simply as you probably anyone here in that webinar has done at least one linear regression exercise in their word. I don't want to get into the debate whether linear regression is considered a machine learning or no, but it to me it simplifies the idea of a machine learning. You find a relationship between a parameter X and parameter Y, and then you have some data, and then you can find a relationship, which is that red line. And then later, when you have any new point you would like to see what's going to be the expected outcome given the X value, you can use that red line as your formula. So you have a data set, you have some inputs as predictors, you have some observations, and then you have the outputs that you are getting to predict. And if you simplify it graphically as a kind of like a neural network style, it is just in a so have three inputs here, x1, x2, x3, and they all translate into y, and every line here capture like a parameter relationship such as linear regression. But if we get a more complex data like this, can we really approximate it using the same simple linear regression? It will likely fail. It will generate a linear line like this. But if we increase the complexity, maybe that's a nicer trial. And if we increase it more, maybe that's a lot better. And if we increase it more, now that's capturing a lot of the dynamics here. So think of a machine learning or a neural network as a function approximator. It's something that whenever you try to reasonably increase the complexity and play with some knobs, it will allow you to fit some function and will allow you to then make a reliable prediction. So now thinking about this, how do we use this in our field? Now that's data-driven modeling or machine learning. Now how we could use it or how does it compare with other modeling paradigms that we have? So it doesn't come without challenges as everything. So now if we compare that data-driven models with the first principles that we talked about and maybe the semi-empirical, and we have some aspects to talk about, maybe the amount of physical knowledge being embedded, and that translates directly into the interpretability. How do you understand the prediction being made? And now the extrapolation power, how far can it go and extrapolate in the future or outside of the range? And now you have the data dependence, and now we have the deployment readiness. So if we look about this, you're going to see that the first principles models, they are really like almost all the physical knowledge that we know is embedded into that model. That means it's highly interpretable because you can understand whatever is going on because you know all the equation. You can track how this prediction was being made. And you could extrapolate because it's based on some reliable knowledge, so you could extrapolate in the future. It really has low data dependence, but it also has low deployment readiness because it's computationally heavy. Semi-empirical, everything is a little bit less than the first principles, but on the same line. But if we thought about data-driven, it's completely the other way. Almost no physical knowledge being embedded. That means another also low interpretability and low extrapolation, but it has high data dependence and it has high deployment readiness because it's normally easier to deploy these models in real world. So I will talk about here two examples. The first one is about N2O emissions modeling, and you can see more details about this in the publication that I'm going to share. But that was a system that you were trying to model N2O emissions. And for your background, mechanistic models has always struggled to capture or predict N2O emissions the accurate or the right way. So I will not talk further about the details. I've talked about it several times in several other conferences, but it's simply these input features, and then it was being used using a machine learning model to predict the N2O emissions. And the results were already good in terms of prediction. So the message here I would like to convey is that you don't probably with data-driven models, you don't have to worry about accuracy anymore. Like, with this powerful function approximator, with reasonable effort, with reasonable data quality, you can really generate whatever the accuracy that you're aiming for, probably. But there are some challenges other than this to worry about. So, do we align with domain knowledge? Like, assuming that we already have assuming that we already made the prediction, can we use these predictions to make a decision making? Like, okay, now we see the prediction, we see what factors has made this N2O to be high. Can we rely on the model to go and modify one of these variables, one of these parameters to reduce the N2O emissions or no? But before we go that way, is the prediction aligned with domain knowledge? Because a model can be doing the right prediction, but for the wrong reason. Remember, you just trained this model on only one data set. So it could be just making some spurious relationships or spurious correlation. So what we did here is that we tried to see the alignment of the model with the domain knowledge by trying to understand by trying to mimic and model the relationship between, for example, one parameter like the nitrite and the predicted variable. And we have two versions. One is a complex model and one is a simplified one. And we found that for the complex model, the relationship was really shaky. Like you can find like when you increase even the nitrite with very small amount, you could have like from an increasing value of N2O, it could be really suddenly being dropping or decreasing, and it's not a stable relationship. But this relationship kind of stabilized when we reduce the model complexity. So that gives us an insight like, hey, like the model complexity can have a huge impact on how the model behaves with your data. And these parts were completely removed when we reduced the complexity. But does that mean still the model is relying on the right knowledge? Does it align with what we understand about this system? So if we look about it, did another test like did the feature importance, which is here, like very global understanding of how the system relies on features. But if we try to provoke the system further, remove one of these features, like the most important one, and see how the system behaves, we have found that the system actually trying to elevate the reliance on the DO, and that align too much with the domain knowledge we understand as an overall behavior of the model, because this system was assumed to have, if you know much about N2O, is a nitrifier denitrification pathway. So here what we've been trying to do is try to see how can we interpret the model and then does it align with the domain we understand or no. But again, that's a lumped behavior. That's not a point by point understanding. That's overall the model relied on these features to make their decision. That doesn't mean that still this is the most accurate. We could go another level higher. We could try to get 1 point and try to see why did the model predict this value? And remember here, we're not saying why did this value happen, but how the model made this value, how the model predict this. So we're trying to understand how the model made their decision and see if that aligns with what we understand. And here we investigated the CHAP values, and we found that the model came up with this really high value because mainly relying on nitrite and then relying on DO at location 3 with some other minor contributions. When you do this, we have to remind ourselves that this is not a causal effect. That doesn't tell us that, hey, that means you go and modify DO3 and I guarantee you will have a lower nitrous oxide. That tell us just how the model made the decision. But what if we would like to go more? We'd like to understand no, we would like to understand how the model made the decision, how we do that, how we make decision making ourselves, and what factors can we modify so that we reduce the N2O emissions. That turns into a cause and an effect relationship. And that means we're moving from the global interpretability, passing through the local interpretability, but getting into interventions and counterfactuals, which are causal inference concepts that we need probably to tackle if we need to understand this. And the limitation with causal inference is that we cannot really do it unless we have a physical or a knowledge graph of the system. And if we try to do something like this, maybe that's one trial for nitrous oxide, you get something like this. So you need to have this data and try to really do best practices of causal inference to understand what's happening and how you get into this. But the causality problem is complex. Assuming you only, for example, have DO and you would like to see and DO affects N2O. And then assuming you have only this data set and you have airflow affects DO and then DO affects nitrous oxide. So you really can't estimate the causal effect too because airflow impacts the stripping of N2O. And that statistical problem because now the airflow acts as a confounder. And if you try to get the data and just get the relationship between DO and N2O, that will be misleading because that doesn't quantify the impact of DO on nitrous oxide. Even if you turn it into a probability, it's going to be here the probability of N2O given DO is going to be a correlation. And the right way to do this is to turn it into an intervention problem. What's the probability of N2O given we change DO to this value? It's called the do operator. And that's how we estimate that causal effect. So just here a note, the ML models can easily learn correlations, but extracting causation requires all of that extra work, which for that case, it hasn't been done and it's a work in progress, but this is to give you a realization of what it takes to turn it from just prediction to really an actual causal impact or intervention. Another quick example is about an RO membrane fouling forecasting, and the objective was and that work was done with Modelu. And the idea here was trying to using a data-driven modeling to predict or forecast the fouling of an RO membrane so that it's used as a part of an MPC. And the idea was that because mechanistic models that try to forecast membrane fouling is really heavy or not reliable to really make the forecasting or the prediction that you want. And then same here, an LSTM model was used. It takes the last 6 days of these parameters and it try to predict the fouling into the future, into 4 hours into the future. And then if you look at this forecasting, it really looks good. This is almost how we try to evaluate our machine learning model in addition to metrics. You see that the forecasting looks really good. But if you try to zoom on a period, even like this period that looks really good, and you try to see the results, you're going to see that you're actually missing the point of what you want to do. You would like to be able to forecast the trend or to make an actual decision because how the fouling is going to change in the next few hours. But what's happening here is that there is a huge lag, huge maybe in terms of hours, huge lag between the actual forecasting and the actual data, which is giving you completely the wrong trend. The reason of this because that system is being turned off and on very frequently, and then the data is very hard to interpret. It's very hard to find some meaningful relationship using the sensors when it's being turned off every few hours or every maybe 2 hours. So that was a problem. And if you really got in the illusion of, hey, it's just about some simple accuracy metrics, you will likely miss the purpose of why you're developing this model. And the way that even further, like that model should be reacting to recovery. And because the model relies on spurious relationships, so the model is not real. That's the feature importance of the features being impacting the model, and the recovery is the one that is going to be used in an MPC setting. But you see that the model is relying on the previous resistance, which is the autoregressive relationship instead of just this recovery. And the way that was fixed is that by reconstructing the membrane fouling, by just trying to predict the difference between the delta RM instead of RM. And yeah, and this predicting that delta RM made the model able to get to capture the dynamics to a really great and better extent. And that's because that turned the data into a stationary data instead of being highly non-stationary. And it's able to capture the dynamics of it simplifies a problem even for a power machine learning model to solve. And that was reconstructed back by putting this into that again. So you end up with forecasting the absolute value of the membrane fouling. So it is worth noting that even for a powerful model, the operational conditions, the operational characteristics affect how the model works. It made the predictions were lagged, and the switching to predicting or forecasting the delta RM made the problem a lot simpler and easier to forecast, and then led to a better accuracy overall. Uh, some key takeaways from that about data-driven modeling is that it's part now of our modeling toolbox. So don't think about this being replacing any of the other models, but they solve certain types of problems. The other one is that not because they are very powerful, that means you could just throw things in and get the output as a magical device. No, it needs some consideration about how the model works and how to really frame the problem and take care of the accuracy is not the only metric, and accuracy even can get better for the wrong reason. So try to understand how the model worked and how things went with that model. So I will leave. Thank you. I will leave my colleagues continue their presentations, and thank you for this.
Thank you, Mustafa. I think that was a great introduction to the subject. Remember, you have the Q&A and start posting your questions. And now we move to the second speaker. It is Dr. Kate Neward. She's an assistant professor of environmental engineering at Oregon State University. Her research focuses on applying data-driven and machine learning approaches to improve the performance and resilience of water and wastewater systems. So, Kate, floor is yours.
Thank you, and I apologize in advance, everyone. I'm losing my voice, so I'm going to try to do this as concisely as possible, but feel free to put in the Q&A if you can't hear me and need clarification on a term that I'm using. To a lot of Mustafa's points, data-driven modeling, and especially machine learning modeling, where you have a high degree of flexibility, is wonderful, but also incredibly challenging when it comes to validation. Is what we're observing in our desktop environment real? And so sometimes this requires us think differently about the modeling challenge that we're facing and trying to better align our modeling objective with the problem statement that we're trying to originally solve. And this is all with remembering that machine learning modeling and data-driven modeling is complementary to mechanistic modeling and that they are not designed to solve the same types of problems. So today I'm going to be presenting some work that was completed by myself as well as a PhD student, Joe Liebeck at the University of Michigan, on phosphorus modeling and how we used machine learning to try to address the bigger question of how we do optimization, right, quote unquote, optimization of the system. And that's right when we, chemical input optimization. So through the project, we, kind of generally use this workflow, right? Defining the problem, collecting the data, organizing and preparing the data in a way that can be ingested by models, exploring a lot of different model architectures, because there is no single machine learning model architecture that is universally better for a single type of environmental engineering problem. So it's very much you have to put on your experimentalist hat and play around with different approaches, and then you deploy. Right? Deployment can mean a lot of things. It can mean active control, but it can also mean in an advisory role offline for operations as decision support. But as you collect more data, as you notice, phenomenon that were not in the original simulation study, you realize that now you may have to revise your preparation or how you train your model. And so the results of this work, as well as all the other work done by my colleagues on this bigger Department of Energy project, are available at watermltoolkit.com, including Python notebooks kind of showing all the steps. So if you're interested in getting engaged or involved for the first time in machine learning, that's a great resource. So to get started on what makes a good machine learning problem, a couple of important things, right? You have to think of a specific machine learning appropriate objective, right? So understanding chemical kinetics is not a key feature of machine learning, right? Capturing maybe the effect of chemical kinetics for the purpose of optimizing energy, yes, that's a good machine learning objective. With that, do we have some sort of measurable improvement performance criteria? So by what percentage do we need to reduce energy consumption in order to merit this model being worth deployment? Because one of my favorite papers I read when I was first going down this journey was it did a beautiful neural network development for a DO controller. But the very last line of the results section said, and then we properly tuned our PID, and all of the benefit of the neural network, vanished. And so understanding what it really is going to take to give better value to the water sector, this number is important to understand. Because what is just an artifact of the data, what is meaningful improvement. And then finally, implementation has to be integrated into model design. So what data you're going to have available is incredibly important to understand. So here's our system, right, for phosphorus recovery. This is at Metro Water Recovery in Denver, Colorado. So like many utilities, they do BioP. And so they have a high concentration of phosphorus in their biosolids, which after digestion ends up leading to a lot of precipitation of the phosphorus product in their pipes, which leads to tens of millions of dollars a year being spent on pipe replacement and management. And so what do? Right, you try to put in a controlled struvite precipitation reactor. And that's great because now you can generate a beneficial byproduct that can be sold as a fertilizer, and you reduce maintenance and you reduce truckloads. Everybody wins. But so here's an example of the struvite precipitation reactor, Magprex. It's a delicious matrix, as you can see, but you can also imagine not a lot of sensors can live in this matrix and give us accurate data. So to control this, we're adding a reagent, right? So mag chloride, and doing a pH adjustment using air stripping. So those are the two control levers that we have for the system. And right now, operators are just kind of guesstimating They kind of, go in, they take a sample 2 to 3 times a week of the effluent phosphorus, and they're able to target an ideal effluent top phosphorus that doesn't affect the BioP and does not assume an excess of reagent adding. And that's about 30 milligrams per liter for Metro. So why don't we have more advanced controls here? The only model that we have, the only mechanistic model that we have is just a very generic mass balance and chemical kinetics model. And it's terrible at predicting. We don't have a lot of online data, right, as you saw. And so you're very much reliant on this operator specific, site specific knowledge to try to optimize or tune in this model. Hence why you can see how machine learning is now, potentially an avenue to better optimize the system. So kind of revisiting where we're here. I hear this a lot when I work with utilities. Oh, I have so much data. Well, that might be true if you're using instrumentation data, but as soon as you get to using laboratory data, you suddenly have to condense down your data space significantly, which means you may not have as much data for training as you thought you did. And so in this case, those black bars are where we're missing data, and some of that's really important data like phosphorus and ammonia species, which we know mechanistically to be tied to effective struvite removal of the system. So when we start asking these questions of, can I apply these standard data science principles, so what we learned from computer scientists and statisticians in the machine learning space, to environmental data sets, we now have to think about data sparsity, distributions, things that us as practitioners know intuitively, but I think we see machine learning and maybe get a little scared and don't trust our intuition. So I want to encourage everyone to be a machine learning practitioner and trust your instincts as you go through the process. So this is actually a different project, but just as a segue for why it is so incredibly important to understand the properties of the data that are being generated by your system. This is just an example of a spectrum of different statistical and machine learning models and the model errors. And basically, if you take conventional data science practices in orange, versus if you consider, in this case, the time-dependent component of some high-frequency data collection, just 3 hours apart, right? So not, sensor high frequencies, it's still lab data. But you can see there's about anywhere from a 25 to 50% difference in the errors. If you use a subject matter informed data preparation schema across all model types. And so what does this mean? It means we get a lot of folks who don't know their environmental data going and training a model using conventional data science practices, a random 80, 10 split. They tell the utility, hey, I have an amazing model, that can predict, in this case, your phosphorus removal. But then they go and deploy it, and the errors are upwards of 50% greater than what operations intended. So what do? They just shut down the model. And a lot of times now you have burnt a bridge with a utility that is now less likely to invest in machine learning development in the future. You've wasted a lot of time and you really haven't contributed to the greater body of knowledge. So this is why I think we've seen a stagnation in work in this area. And so I am very intrigued in understanding what the relationship is between the properties of our environmental data sets and how they impact our modeling practices and how they can impact our final models. And so just kind of as an overview, this is what we ended up working with for the MAGPREX, the phosphorus recovery system. We ended up trying to predict 3 different things. The influent phosphorus, that's what's coming out of the digester. The effluent phosphorus, so what's coming out of the MAGPREX in the liquid stream. And then the difference between the two of those. So the OP that is removed. Remembering that kind of Metro is aiming for a goal effluent phosphorus, still orders of magnitude less than influent phosphorus, but we kind of wanted to see what the model could do. We didn't do any interpolation, right, to this point that you don't want to have a data leakage problem where we're giving the model more information than it would have in a deployment scenario. We tried various feature selection options, try to reduce the number of input features because we have such a sparse data set. While some of these models are really good and robust against additional features, some of them are not. Obviously trying a spectrum of different model complexities because we don't know, right? There is no universal model. Doing a robust, sensitive to the data set cross-validation and model evaluation, and then deploying the model and understanding how it deploys in real time. So now moving on to the three different models and evaluating the results. So these are effectively on the x-axis, the number of inputs to the model, and on the y-axis, the model error for influent phosphorus, effluent phosphorus, and phosphorus removed. And what I want you to take away from this here is that there's actually a lot of overlap between some of the simple statistical models and some of the advanced machine learning models in influent phosphorus and phosphorus removed. But effluent phosphorus, the machine learning approach, is by far superior. And this shows, once again, the impact of the additional features in those data preparation steps, but also the importance of exploring all of your possible options. And especially when you put in the confidence intervals here, right? So considering the total variability that we saw in the errors of the data set, there is no statistically significant difference between the linear regression and the XGBoost model for influent phosphorus and phosphorus removed, right? So what is this telling me? I don't have enough information in my data set for XGBoost to be an effective tool, right? But I do for the effluent phosphorus. So that's kind of the one that we kind of targeted moving forward in the next step of our project. And just for, completeness sake, we can also look at the pairwise plots, but the pairwise plots actually look pretty good, right? If we were to compare it to the plots that I just showed. So we have to remember that how we tell the whole story is incredibly important. But we can also see that not all of the errors are evenly distributed across the range that we're interested in. And so moving forward, what happens when we actually deploy? So this is the model is on Metro's server, right? It is taking real-time data and making those predictions, right? So I am not doing anything from a modeling perspective now. We're just sitting back and watching. And what we can see is that, once again, influent phosphorus and influent phosphorus of the top plot and the bottom plot, phosphorus removed, we miss that major perturbation in the system using the modeling approaches. But we are able to capture it in effluent phosphorus. So as you can also see, there's a little bit of a data gap before the poor model performance. So the reactor was shut down. So this is startup conditions. So now kind of thinking a couple of steps further, right? So now we have this very unusual influent condition in this very unusual condition, non-steady state within the reactor that the model may not be capturing very well, but the effluent phosphorus was sufficiently stable that it was able to be captured. So what do we do now, right? But think back to our original objective, right? I wanted to be able to reduce my chemical input. That's really all the utility cares about. We're not worried about mechanistic understanding. So when I am now looking at this, how can I refactor my problem to think, well, I can't predict mag chloride. Trust me, we tried. But because operators had kind of tuned it in, it didn't give us any valuable predictions there. So now we thought, okay, well, if I can predict effluent phosphorus, maybe I can give operators a tool that says if I have high effluent phosphorus, that means I need to increase my dose. And if I have low effluent phosphorus, I need to decrease my dose. So that's kind of what we're doing here in this plot, where we can see in the second quadrant, if we're predicting an elevated concentration, increased dose, and a lower concentration, decreased dose. And you might ask, well, why don't we then use that difference, so the numerical response from our effluent phosphorus regression, to inform that the mag chloride reagent concentration? Well, you'll see that there's actually quite a large, not just variability, right? So a difference from that perfect line, but the magnitudes. You try to go tell an operator that they need to start change their concentration by 10, 20, 30 milligrams per liter, they'll look at you like you're crazy. And so from a feasibility standpoint, that's why we decided to actually move towards a classification-based approach. So even though we're still using a regression model to derive our original response to operations, if we look at this through a classification lens, so just does my data point lie within one of these quadrants, our accuracy actually becomes pretty incredible. So we end up being correct in as far as the direction that we want the model to go 97% of the time. When we think about practical implications, the operators are always going to be making the determination of how much they're willing to adjust the mag chloride concentration by anyway. So this is a great middle ground that meets our objective, that is sound statistical science. And so it's pretty awesome to see. But when we do the calculation for how much we actually save, it's actually not that much, maybe 5%, because, right, operators had already kind of tuned in this model pretty well. So we have time on the x-axis here, concentrations for both the mag chloride reagent and phosphorus on the y-axis. The phosphorus, the effluent phosphorus is in green, and that goal of 30 milligrams per liter is that line across the bottom. And you can see that for a while, they were actually overdosing. So there's a little bit of savings there, but a lot of the savings is in robustness, right? A lot of the ability to keep a steady state system. And so it's interesting when you try to consider the business case behind some of these projects that I work on, because a lot of times the business case is not in energy savings, but the business case is in an increased resiliency, an increased robustness, and improved operator response time. And that can be difficult to sell. From a business, from a capitalistic standpoint, but it's incredibly important when we think about longer term changes and being able to respond to climate change or population dynamics or other, potential future challenges that utilities are seeing. But what we also want to be aware of is the data space, right? So if I have only operated my system, right, within an effluent phosphorus of, in this case, about 60 to 5, that is the effluent phosphorus that my model is going to be able to predict, because to Mustafa's point, these models cannot extrapolate well, right? If anyone has tried to ever calibrate a conductivity probe, so that's in the upper right quadrant there, we all know it's beautifully linear up to a point and then it's just gone. So you very much have to think about what is the data that is represented in your machine learning model. And here's a piece of evidence to kind of support that. So in this case, we have influent phosphorus on the left-hand side. This was using a classic ridge model, so a statistical model, and then effluent phosphorus on the right-hand side using the XGBoost model. And model errors are on the y-axis, and the percentile of the concentrations are on the x-axis. So low concentrations are in the lower percentile, high concentrations in the higher percentile. And what we can see here is the machine learning model. Basically, if you're in the 0 to 20th or 80th to 100th percentile, the model's terrible. We're not even talking about extrapolation at this point, right? We're still talking within my defined data space. My errors are just really bad. And then the statistical model is a little bit better, right? But once again, 80th to 100 percentile, terrible. So we're still, despite a multi-year sampling campaign that Metro was not willing to continue to invest in, beyond the research scope of the project, because there was hope that this would help augment some of the sampling requirements. We still just did not get enough data. So the answer is, we'll just get more data. That's not an option. So you have to really think about, when you're working on a problem, what's my overarching problem? And put on that experimentalist hat and try a lot of different ways to try to achieve that objective, given the deployment conditions that you're going to see in the real world, because you'll find some incredibly interesting things within your data, within your system, and identifying ways by integrating the operations team, the engineering team at every step along the way is incredibly important to identifying these findings, creating models that are resilient against some of these drawbacks, and understanding what the limitations are and expressing those so that you can have good fallbacks or good safeties when you do exceed, right, the regular percentile ranges that you have confidence in. So big research question coming down the line. How do you build these data-driven models in data sparse spaces? So we've now kind of completed the whole cycle, right? The model is still running. We're still collecting data. It's still an advisory tool, but we know that it can be better. So hopefully you've learned that machine learning models are great in, capturing that non-ideal, highly nonlinear behavior. But as much as data are your solution, they can also be your problem. And so you always have to be very wary of artificially low errors or very, very high accuracy to ensure that there isn't a data leakage problem where maybe some of your training information has leaked into your testing set. I see this a lot with when you have to interpolate data or when you have a very high frequency time series data, or if you don't sufficiently lag laboratory data, right? Because they might take a sample they will get it 24 hours later, but they'll still mark it in their system as received on day one. And so understanding some of those dynamics can drastically affect what your final calculated errors are before deployment. And so, with all of those things in mind, even though it seems scary, when you look at it as a team effort, when you look at it as let's include all of the users of our model, and you look at this as we will figure it out, those are the most successful utilities that I've seen and the most interesting projects. And we discover a lot of new things about environmental data science that way. And with that being said, I do want to throw out that I am currently hiring PhD students. I'm looking to hire 2 PhD students for this upcoming fall. So if you are interested, feel free to email me and look at the Oregon State University Environmental Engineering PhD application on the Oregon State University website. Applications close in January, so reach out soon if you are interested. And with that, I'm going to pass it off to Elena.
Good, thanks, Kate. Very nice example that you showed us. Now we move to Elena. Elena Torf is an assistant professor at Université Laval in the research group of Modelo, and her research focuses on the connectivity between data models for the development of digital twins and advanced control algorithms. So, floor is yours. And remember writing your questions. We have one, so looking forward to questions for Kate as well.
Thank you, Luis. Can everybody see my screen and hear me? I hope so. Okay. So for the last presentation, I want to talk about how do we integrate domain or process knowledge within data-driven models or machine learning. So we've talked a lot about, indeed, the paradigm change, going from mechanistic models to machine learning models, the benefits and pitfalls of machine learning models. But of course, the idea of this presentation is to explore a bit like how can we optimally take advantage of these emerging data-driven models while still having all the advantages of the domain knowledge and the process knowledge that we already have. Okay. So as Mostafa introduced, is historically we've been mostly using mechanistic models based on first principles, which are either fully based on first principles or including some empirical equations in there. But many of those are maybe limited by knowledge, don't have too many simplifications, don't have all the relevant process in there. So we see that they don't always give good results. Of course, alternatively, we have data-driven models, which are completely based on data and will learn their model structure from the data. Of course, these are limited by the data themselves and struggle with things like extrapolation and interpretability. So over recent years, there's been also search in ways to combine these two paradigms, and able to, of course, make use of the advantages of both, the robustness and the interpretability and the process knowledge in the mechanistic models with the flexibility and the ability to learn from data in the data-driven models. And that leads us to what we've been calling hybrid models. So hybrid models, a way to combine mechanistic and data-driven models together to take advantage of both paradigms. But hybrid models is only one way to incorporate more domain knowledge into machine learning or data-driven models. I think what I would like to do in today's presentation as well is to zoom out a little bit and to talk about scientific machine learning, it's called, so SciML, which is a bit of a bigger domain that incorporates hybrid modeling, but that goes beyond. So for instance, what does scientific machine learning entail? So the idea of scientific machine learning is to indeed to incorporate domain knowledge and domain robustness into machine learning efforts. So to incorporate scientific computing, domain knowledge, science in general into machine learning, with the goal to achieve scalable, domain-aware, more interpretable machine learning. So as I said, hybrid modeling is part of scientific machine learning. So hybrid modeling where we combine mechanistic and data-driven models in some way. But you can also, but it also includes surrogate modeling, for instance, where you will use machine learning to train less complex models or less computationally expensive models onto mechanistic models. Equation discovery, where we use data-driven techniques to actually try and learn equations from your data, but interpretable equations. There are physics-informed neural networks and so on. So many different methods are included into scientific machine learning. And I think hybrid modeling is the one that has gained a lot of maturity over the last year, but I think it's interesting to look at the other types of other methods that can incorporate more domain knowledge into your machine learning or data-driven models as well. Many of these topics are not new. So and this is a journal paper from 1994. So that's more than 30 years now, in which they talk about some of these things. So how to combine prior knowledge in this paper with artificial neural network models. But of course, we can extend this to any machine learning or data-driven models. And you see that there's two pathways. One is to have your knowledge into your model structure. And then this is what we typically do in hybrid models. So we join some kind of mechanistic model structure with our data-driven model structure. It can be done in several configurations, serial, parallel, combination of both. So I'll talk about this a little bit more in a second and give some examples. You also have the option of including the prior knowledge within your training approaches instead of within your model structure. And then, for instance, specifically, if you include mechanistic equations or mechanistic knowledge into your objective function, your loss function for training your neural network, then you come into the field of physics-informed neural networks, or the PINs. What is not here, but I think is also an important branch of scientific machine learning, is the whole scientific model discovery and refinement. So really using machine learning techniques to build new models, build simpler models, or build more interpretable models. So I kind of put three things here together because I think they all in some way try to discover or refine models. So surrogate modeling, symbolic regression, and maybe some enhanced data assimilation. So I will start by talking a little bit about hybrid modeling, what has been done in the recent years, the different architectures and some challenges. And then I will try to go a little bit into this, I think, interesting field of more model discovery that we can do. Okay, so when we talk about hybrid models, there are several architectures, several ways in which we can combine mechanistic and data-driven models. So we have, if we think of two classes, serial and parallel models. So in a serial hybrid model, you will have first a data-driven model, and the output of your data-driven model will be fed into your mechanistic model. So it will be an input for your mechanistic model. In the parallel approach, you will actually have both mechanistic and data-driven model in parallel, and you will sum their two outputs together. Let's see a bit what this means exactly. Maybe a little side note. When it comes to hybrid modeling, the International Water Association has a very active working group on hybrid models. And they have started an initiative to collect, review, and publish some examples of hybrid modeling. So through the link here, it leads you to this QR to a GitHub page where you can find the first example with all the code, so that can really, if you want a practical example of how to build a hybrid model, you can find one there. And the idea is to extend this in the future. If you have case studies that you think would fit in this, feel free to reach out also to me. Okay. So let's first look at parallel models. When would you use a parallel hybrid model? If you have incomplete knowledge in your mechanistic model or some oversimplifications, but you don't really know where in your mechanistic model. It's very difficult to pinpoint where exactly it is. So you will do kind of an overall compensation with your data-driven model for accuracy gains. I will give a little example of work that was done at pilot wastewater treatment plants. So this is our pilot pilote, because EAU is water in French. The pilot water resource recovery facility at the Université Laval campus in Quebec. So it takes water from the residents the student residence. It has a pumping station in the sewer network of the campus. It goes to a storage tank, primary clarifier, and then it has a typical 2 anoxic basins, 3 aerated basins, an internal recycle, secondary settler, and a sludge recycle. So what we wanted to do is to build a hybrid model to better predict the nitrate concentrations in the effluent. So this was something that our mechanistic model was struggling with a bit. So we were looking into a hybrid model to do this. So this was work done by Loes Verhagen. So what she did is, first we had a mechanistic model in West that took the traditional influent and predicted a certain concentration for the nitrate effluent. So we combined this with the neural network that it was trained to predict the error on the nitrate concentration. So the remaining error between the mechanistic model and our actual pilot plant data. So we combine both, we sum them together, and we have a hybrid model for the nitrate effluent. So these are some results where you see on the top the training period. For the little dashed line, the most dashed line is our measurements of nitrates in the effluent. And then we have the longer dashed line is the calibrated mechanistic model output. So you see, and then we have 2 types of hybrid models, one where the data-driven component was an LSTM and the other where it was a convolutional neural network. You see in the training period that all models kind of work well. But if you look at the testing period, then you can see that, first of all, the calibrated mechanistic model doesn't perform that well. So it was probably overfit to our training data. And that also for our 2 hybrid models, in this case, the convolutional neural network model worked best. So this worked quite well. But of course, when you look at parallel hybrid models, there's 2 big challenges. First of all, you only compensate at the end of your mechanistic model. So you don't really learn a lot from what is missing. You cannot really learn a lot from it either because you're not closing your mass balance. You're only compensating for the final error. And what I mean with not closing the mass balance, if I go back to our case study here, so we are training a data-driven model on the effluent nitrate concentration that is wrong in the mechanistic model, but there's no feedback loop from that data-driven model to our mechanistic model. So if this effluent concentration is wrong, that means that the internal recycle is also wrong. So in theory, should also be compensated. And so this we are not looking at in parallel hybrid models. So you see, there's no feedback from the neural network model back to the mechanistic model, which means that we are not closing our mass balance. We're only just compensating for an error at the end. Second challenge is balancing the calibration efforts. So you need to calibrate the mechanistic model and a data-driven model. But how much calibration effort do you put in both? In this case study, what we observed was if we build a hybrid model using only standard parameter values. So in the mechanistic model, we got better results of the final hybrid model than if we first tried to calibrate the mechanistic model. So the idea is, if you over-calibrate your mechanistic model, if you overfit it to your training data, it will be more difficult to actually build a hybrid model, because the hybrid model doesn't only have to learn missing dynamics, it also has to learn the mistakes from the overfitting in your mechanistic model, which is not really easy to do. So this balancing of calibration efforts when you are combining 2 models is still a big challenge, for which I think at the moment no real methods or recommendations exist to figure this out. Okay, let's look at serial hybrid models. So here we will have a data-driven model that feeds into a mechanistic model. When is this mainly interested? If your overall mechanistic model structure holds, but if you have a specific sub-process where you have high uncertainty or that you know is insufficiently defined, so you really want to focus your data-driven modeling effort on that specific sub-process. I will give an example of a reverse osmosis case study, where we were build a hybrid model to predict like the concentrations, pressures, then flow in both the permeate and the concentrate of the RO installation. So we had a mechanistic model, a solution diffusion model, that had a lot of processes well described, like the osmotic pressure, the concentration polarization on the membranes. All of those were well described by the mechanistic model. The only process that was not well described by the mechanistic model was the fouling of the membrane. And we could, from the sensor data that we had, calculate the membrane resistance. So we trained a data-driven model, in this case again an LSTM, so a long short-term memory model, to predict this membrane resistance with inputs temperature, conductivity, flow rates, the recovery rates, there are calcium concentrations upstream, and the cleaning in place that was done of the membrane. So we built a data-driven model to predict this membrane resistance. And then, of course, we had to find a way to couple this prediction of the data-driven model to our mechanistic model. And what we did is we coupled it to 3 parameters from the mechanistic model that we know are fouling sensitive. So the water permeability, the solid permeability, and the spacer thickness. And we created connections either from literature or through some simple empirical equations. You can see here a bit of the results where you see in light gray the data for the concentrate pressure in this case, and then in darker gray the results from our serial hybrid model. And you see that it works well for about 2 months and then it completely deviates. So there is a need for retraining or some things that are not captured sufficiently in the data, so that the time scale over which this remained relevant was limited. The black one here, I will come back to that later. That's still a bit of a teaser for now. One advantage of serial hybrid models is that they allow you to incorporate other data sources that are maybe not so easily to incorporate directly into a mechanistic model, but that can bring relevant information. So this is something that we've tried as well. In this case, we used microbial images in a data-driven model. So through a convolutional neural network, we automatically extract features from these images, and these features can then be linked to a certain uncertain parameter in your mechanistic model. We've done this for KLA to better predict aeration, and we've done this for settling parameters as well. And for both, this gave quite decent results. So these are the results for the KLA. Where in blue you have our measurements, which were calculated from our lab data and sensor data in the pilot plant. So from that we could calculate the KLA. Yellow is the training results for the hybrid model, and then red gives us the testing period. That brings us to a very, very big challenge into serial hybrid models, is their training. Of course, in the 2 cases I just presented, we were very lucky. We had some intermediate value that we could calculate or that we could derive from some measurements. So we had the membrane resistance that we could use for the RO case, and we had the KLA that we could calculate from our sensor and lab data. But in many cases, this is not the case. Imagine that you want to build a data-driven model to better predict some kind of growth rates in your system. This is not something that is easily measured. So training of serial hybrid models is a challenge because of this. Now, there are 2 options to do this. If you don't have this intermediate variable available, not measurable, and not able to calculate it, you can take a 2-step approach. So you can do first a dynamic parameter estimation of your parameter of interest in your mechanistic model, so which gives you like a time series of this parameter and it's how it varies in time. And then you can use this dynamic time series of the uncertain parameter to train your data-driven model on. Option 2 is to train both components together. So instead of trying to derive this intermediate variable, to just train the both components together. Then we come into the area of universal differential equations, because in that case, of course, your data-driven model will be incorporated directly into your differential equation. So this is what we call hybrid neural differential equations, another form of hybrid models, or also called universal differential equations. So where indeed you have your differential equation, you have some mechanistic component, say a monokinetics, and you add a data-driven component in there. You can sum both up, but you could also, for instance, just replace an uncertain parameter, for instance, your mu, with a neural network. So you can do this in both more a parallel configuration or a serial configuration. But for both parts, the interesting thing is that your data-driven component is directly within your differential equation, which comes with some significant advantages related to the fact that you can do continuous time modeling then instead of discrete as in neural networks. You can, since you train everything through your ODE solver, it's very good, very well able to handle irregular data. For instance, if you have sensor data combined with lab data, because you don't have a fixed time step in this, you can handle both. And because you learn actually dynamics instead of absolute value, it becomes more interpretable, your data-driven component. Of course, the big challenge is training, because you need to do your training through backpropagation of your neural network, but that backpropagation needs to be done through an ODE solver at each iteration, which makes it very computationally not so interesting. Several methods are available or being developed to tackle this a bit, but it stays a bit of a difficult training process. So to come back to the RO case, the little black line that was undefined earlier, that was modeled with a hybrid neural ODE. I have another example here of some very nice recent work that has not been published yet, but from the group in Eawag, the group of Andy Frummelt with PhD student Florian Wenk. So they have been working on this idea of universal differential equations to see how we can optimize N2O predictions. And like I said before, the nice thing with the neural ODEs is that the universal differential equation, that they do include mass conservation, and that the learn process can be extracted and interpreted because they learn the dynamics also. Some first results where they relearned the denitrification process. So here's the NOx concentrations and compared their hybrid model based on universal differential equations with the default ASM3. And also here for the ammonification rate. So they are now applying this to N2O emissions, where there's quite some uncertainty still in the mechanistic models, and they have a multi-year, multi-plant data set. So soon, hopefully, we will see more results from this work. Okay, let's come back to this slide on scientific machine learning. So we talked a lot about hybrid models. I will not go into too much to the physical informed neural networks. There are some examples in literature, although I feel like many are in drinking water networks or more like water quantity description, hydrology, hydraulics, with respect to like wastewater treatment, drinking water treatment, so more treatment processes. There's not that many examples yet there. So this is maybe something where the potential is still a bit underexplored. But for the third branch, scientific model discovery, I do want to talk about this a little bit and give some examples. So the first one is about surrogate modeling. So the idea of a surrogate model is that you have a very complex model, which is maybe computationally too heavy for certain applications, and you train a more simpler data-driven model onto this that should, in theory, retain all the crucial elements of the complex model. So this is work done by Juan Pablo Gallo. And the idea was to build a surrogate model or to have a better prediction of junctions in drinking water networks. So typically in drinking water network models, these junctions are just considered as ideal mixing, whereas in practice, if you have two flows coming together at different flows, different concentrations, maybe different temperatures, then this mixing here at the junction will not be ideal, will not be uniform, but it will be unideal, slightly skewed in one or other direction. So the idea was to build a model that can predict the ratio of the outlet concentrations of such a junction. We have several junction types. So what was done is to build a CFD model of these different junction types, and then many scenarios were run for a lot of different parameter spaces. So considering different ratios of the inlet concentration, considering different ratios of the inlet Reynolds number, outlet Reynolds number, different diameters, and different separations here in this middle junction between the incoming and the outgoing pipes. In total, I think there was about 100,000 scenarios that were done. And then a neural network was trained on this CFD model. The advantage of this neural network is that this could then be integrated into existing drinking water network models like EPANET And this is an example of a result from EPANET, where you could see here in colored the pipe connections where there was a big difference between the EPANET simulations considering complete mixing and the simulation performed with a surrogate model. So you can see that there's a section here that is quite sensitive to these mixing dynamics, and that there was up to 50% difference with a case where it was considered ideal mixing. Last thing I want to talk about is equation discovery. So we've worked on this a very little bit. So the nice thing with one of the advantages of hybrid modeling, one of the advantages specifically of serial hybrid models and universal differential equations, is that you have this neural network that you can actually go and analyze afterwards and see what did it learn, what did it compensate for in your mechanistic model. So the idea is that you create a mechanistic model, you add a neural component, and you train your hybrid model. So then you have this kind of form. But then, of course, this neural network, you can actually go and analyze. So this we've done with Shapley values. And then you can analyze what you learned from these Shapley values. So you can see from this Shapley analysis which, how your neural network, what it learned, how much each of these variables contributes to the output of your neural network. And you can see that you can derive some dynamics. You can see, for instance, some exponential kind of functions. You could see some linear functions. So from this, you can learn and you can see which dynamics seem to be very obvious. For instance, here, like some kind of linear equation between the nitrate concentration and the heterotrophs. So you can try to add this linear equation to your mechanistic model and rerun, so identify missing dynamics, and then restart the whole process. So you again train a hybrid model, but now with a little improvement in your mechanistic model, you again do the Shapley value analysis and you again analyze it. It worked well in the sense that we could discover a lot of the missing dynamics, but of course it's a very time-consuming and very iterative process. It takes a lot of expert knowledge as well to be able to interpret these Shapley values. So it would be nice if we could somehow automate this and automatically do equation discovery from our neural networks in the hybrid differential equations. So there's quite some methods for this that exist. I think there's a very nice paper on from Song et al. on data-driven discovery of governing equations, but in geosciences. So there's some sparse regression, some genetic programming. I only took a few, where the idea is indeed to try to train different types of data-driven models. So in this case, for instance, a sparse regression that will on your data-driven component to really try and see which empirical or physics-based interpretable equations can I fit on these data. So you would have some candidate models that you then see through a regression, which of these candidate models, for instance, a linear, a quadratic equation, which one is relevant for my data. I think this is a topic that is still underexplored, but this is a very valuable for the future of this integration of machine learning into existing models, or to deploy them in practice, also to really work on the interpretability and to learn from our models and not just apply them to a certain case. So for takeaways, what I want to say is that I think that scientific machine learning offers many methods that can help incorporate domain knowledge into data-driven models. I think that the hybrid models are already quite been maturing. I think there's other parts like the incorporating domain knowledge in the training approach and also the scientific model discovery methods that are a bit underexplored in our domain. Each method comes with some challenges and some advantages. And that brings, I think there's one big overarching challenge to this, is model selection. It's how to decide which kind of model or which kind of methods to use to incorporate your domain knowledge. Will you go for a hybrid model or not? What kind of architecture in the hybrid model? So I think guidelines on model selections are really needed. And there's been a first initiative now launched from the hybrid modeling working group, together with the good modeling practice working group, to start working a bit on this on these guidelines. thank you. That was all for me.
Great, excellent. Yeah, we planned for an hour and a half, and it's just 3 minutes to go. We have a few questions, and I think the second question, which relates to Elena's work, I think was about the hybrid and parallel, this hybrid parallel architecture, but I think it was already responded because somebody already mentioned that maybe the solution is the universal differential equations, and then Elena talk about that. So my feeling is that that is already mentioned there, right, Elena? Do you see this is in the chat? So I think, yeah, it came in the presentation then. Yeah.
So I'm just, yes, okay.
So I think somebody was really following your presentation and you gave the right answer just after that. So let's go back to the the other question. There was one question to Mostafa. Can you give some more details on or insights on how to achieve causality with a conditional probability approach, particularly on what type of results are expected?
Yeah, thank you. That's an interesting question. So the causality is actually a big field, but I will give just general insights about how generally you could do that. So the first step is you always have to have a directed acyclic graph or a knowledge graph of the problem you're trying to solve. And then the idea of causality is that you always try to block the confounder or condition on the confounders. So there are some solvable causality problems and there are some unsolvable causality problems. And it all depends on how are you able to measure the confounder or you're not able to measure it. So if you're not able to measure the confounders at all, that means that's not solvable causality problem. And you will not be able to do that. And the only direct way to do it is not from data, is to go and do experiments and be able to measure that confounder in experiments. But if you would like to achieve causality from observational data, which what we're trying to do, you have to make sure that you have the confounder being measured. And if it's being measured, then the steps are pretty much clear. You go ahead and draw that knowledge graph, and then you follow any of the causal inference methods like the backdoor block methods or the forward door block method. And there are even, the idea is to build a structurally causal model using your data and relying on your knowledge graph so that you can then achieve any conditional probability you achieve after that, if you follow the right practice, it's going to be causal probability, not just a conditional probability, because you blocked the confounders. I hope that helps. It's a complicated topic, but it's just giving you a quick idea about how it should go.
Okay, thank you. So there's just a recent question on from Pompilia asking any resources on combining ASM3 with machine learning for wastewater treatment?
I think the work that Andy and Florian and Ewa are doing is using ASM3, or they've done some work on that. Most of the work that we've done is with ASM1, but the extension to ASM3 is not, I mean, not so complicated. So it depends again on the structure of your model as well. If you want to do a parallel model, it's yeah, you can change your mechanistic model by any form. If you want to do a serial model, it depends on which parameter or something that you want to compensate for. But I would look into the examples that are already there on the GitHub of the hybrid modeling working group. I think there it is done with ASM1, but I think it would give you an idea on how it is combined. And of course, the mechanism also holds for ASM3.
Yeah, another one. Can we combine two machine learning models, stacked ensemble for smaller data sets? What do you think? Question from Musavir Rafik.
I'm thinking this is more for Mostafa or Kate. So,
Yeah, do you want to go ahead?
I mean, it entirely depends on the objective. So I think it's an option, but I have not done it myself. Mustafa, do you have any comments?
Yeah. I guess it's like stacking this in ensemble models. Stacking is part of it. You could definitely achieve that, but you should. It's kind of like a meta learning approach. But the idea with the approach is that the dangerous part of this approach is that you have to be aware of the complexity. Increasing the complexity that much with two machine learning models building on each other with a small data set gives you a very high risk of overfitting and the like of capturing just spurious correlations out of this data set. So stacked ensemble is a very efficient approach, but you have to make sure that you feed it with the right data set. Like it shouldn't be the ratio of complexity to data volume shouldn't be really that high so that you really don't go into the risk of overfitting. That's only my take.
Yeah, good. Um, and maybe to just okay. That's you are responding to the question, Elena. And maybe to conclude, I was about to ask. Elena was mentioning some good modeling practices, and Kate was showing kind of a diagram of a workflow. So, what is the status? So, for anyone willing to get into this topic, is there ongoing discussions in the I think is it a task group or a working group on producing some guidelines for this data-driven modeling? What's the status on that?
There's some initiatives from the hybrid modeling working group to work on this. We need to look into good modeling practice for hybrid models, where you take some of the challenge of like how do you balance calibration efforts between two models? How do you select the right architecture? How do you select which data-driven component you will add? Like some of these questions. We've had some workshops on this, but I think there has not been that much of a concrete output, so more like ideas that have been maturing. There will be another workshop at WWRMOT jointly with the Good Modeling Practice Working Group. So the idea was to maybe do this more jointly. And there's been some discussions with Mostafa as well to say like, okay, but it doesn't make sense maybe to only do it for hybrid modeling. Maybe we should indeed see which parts are relevant for all of the modeling paradigms and where do they maybe differ. So that I think this will be a topic of research for the development for the next years.
I agree. I feel like this question of, well, where's my textbook? Where's my, very simple pipeline? That's the question's been asked for 10 years. And I think we're just uncovering new opportunities. Not challenges, not problems, they're opportunities. And so I would just encourage those that have a data set that they believe they've exhausted with the traditional modeling approaches to begin exploring, because it's such a plethora of free resources online these days, and with the addition of AI related assistance to help kind of augment some of that knowledge. I think starting with a data set that you have a vested knowledge of and interest in and understanding of those objectives will help you learn the specific subset of data science that's relative, because it's such a large field. If you tried to learn all of data science, right, as it stands today, only a fraction of that would apply to water, wastewater, and only a fraction of that would apply to your specific problem. So try not to put the cart before the horse.
Good, nice. I don't know. Do you have anything else to say? Otherwise, that was a very nice closing, I think, from Kate. Anything to add, Mustafa?
No, thank you. I think that was what Lynn and Kate mentioned. Responding to that last comment was great. I think that's what we're looking for. That covers everything, actually, was in mind. And as Elena mentioned, I was discussing with her about combining not sure if that would be act as a formal task group or it's going to be kind of combined effort of forming of how do we build and document the best practices for how do we use data-driven modeling in water wastewater applications. So it's kind of in discussion how we're going to move forward with this. But I'm sure we will take an action soon, and we invite everyone who's interested and who has the capabilities, the knowledge, or any ideas to share it with any of us, so that we can have more inspiration before we move forward with that.
Okay, perfect. So yeah, I think that has been great. We will share the PowerPoint presentations and the video in the MIA channels, and then we're gonna share with people who registered to the event. Thank you very much to the speakers. That was excellent, not just theoretical, but also practice. We saw it there, and very good like introduction slides and some fundamentals there. So I really enjoyed. So yeah, thank you very much.
Thank you, everybody, for being here. Bye.
Bye.
Right.